Okay, so in this video, we're going to be looking at a comparison of long division with polynomials to synthetic division with polynomials. Now, I have another video that does only long division with polynomials, but here we're going to be doing the comparing these two different processes that you can use and when they are interchangeable and when you have to use only long division as possible. So our first example is going to be to divide x squared plus 8x plus 15 by x plus 5. Now, if we're going to do this with long division, and this is very hard to type out, so I'm going to draw quite a bit more than I normally do, we're going to basically try to you follow a process that we would normally follow when we do long division with numbers, but we're going to extend it to the polynomial case. There's a lot of similarities if you remember doing long division with large numbers back in grade school. But there are obviously some differences when we're dealing with polynomials versus actual numbers, known values. Now, the setup is going to be very similar. So we're going to take the thing that we're dividing into, and we're going to put it under our division bar. And then the thing that we're dividing by goes out front. Now, one thing to kind of keep in mind is if you are missing any terms, you need to fill them in because that will be a placeholder, which we don't have to worry about with numbers because we already have the placeholders filled in when we're dealing with numbers. And the second thing is that everything should be in the same order. So either descending order or ascending order. In Calc 2, at some point, we're going to be dealing with polynomials that involve ascending order. But for our purposes today, we're primarily going to be working with polynomials in this class in descending order. So the highest degree term will be first, and the lower degree terms will follow that in order. Now, the general idea here is we're going to take the leading term and the leading term, and we're going to divide them into each other. So over here off to the side, leading term of the divisor divided by the leading term of the thing we're dividing with, the dividend. And how does that simplify? That's going to simplify to x. So then we multiply x times x is x squared. X times 5 is 5x. And then we subtract. So I distribute the minus sign through both terms. It is very important to remember that the minus sign applies to both the first term and any subsequent terms. You also have to flip the sign or you're going to immediately go wrong. And then we subtract. X squared minus x squared is 0. But then we have 8x minus 5x is 3x. And then we bring down the next piece. And then we repeat the process. So now we're going to divide 3x by x. So 3x over x reduces to 3. And now we multiply 3x. 3 plus 5, 3 times 5 is 15. And then we subtract everything and we get a 0 remainder, which is fantastic. That means that this divides evenly and our 3 factors, I don't know where my 3 went. My something. My word is trying to be helpful and it is not helping. My factors of x squared plus 8x plus 15 are x plus 5 and x plus 3. Because I got a 0 remainder, then I know that these divide evenly. And so my result is just x plus 3. With, again, no remainder. I don't have to write any remainder after that. Now, how would we do the same process with synthetic division? So I'm going to put in a new drawing canvas. And we're going to, now the way that synthetic division works is we have sort of our divisor bars a little bit modified, and we write the coefficients only of the polynomial that we're working with. Again, in order, if we have any gaps, we have to fill in the zeros. And then the number that actually goes outside here is of the form C if this was a factor x minus C. So in this case, this is x minus a minus 3. So this is actually not the factor number. This is the root. And this extra change in sign is going to allow us to add instead of subtract when we go through our algorithm. Because you remember in the previous one, we were multiplying and then subtracting. And so by flipping this sign, we're going to be able to add instead of subtract. Now, the general process for the synthetic division, we bring our leading coefficient down here, and then we multiply these two together, and we put it here on the next line, and then we add these up. Actually, I'm dividing by the wrong thing, but that's fine. I'm dividing by the solution, and what we should end up with when we do this is the x plus 5 that we started with, since I'm using the other factor. So that'll get us 5. And then if I multiply that, I get negative 15. And then the last term down here is our remainder. If this is not 0, then we have some non-zero remainder. And then this was originally a quadratic, which means the leading term was x squared. We always, because we have to use a linear term when we do synthetic division, we can't use quadratic divisors. We can only do linear divisors with this process. The result is always 1 degree less than what we started with. So our leading term will be x, not x squared. And so our coefficients are going to be x plus 5. So since I divided by x plus 3, my result was x plus 5, and that is because my original polynomial, x squared plus 8x plus 15, is equal to x plus 5 and x plus 3. So regardless of which one you do the division with, you should end up with the other factor as your exact quotient. Now, let's look at an example that is a little bit more complicated, just so that we can see how this works. So let's look at six x to the 5th minus 2x cubed plus 4x squared minus 3x plus 1 divided by x minus 2. So again, we're going to do this with long division first, and then we will redo the problem with synthetic division. Now, again, we can do this with synthetic division because the thing we're dividing by is linear. Now, here we have a missing term. So when we do our synthetic division, I'm going to leave myself a little bit more space. We do have to fill in that missing x to the fourth term. So 6x to the fifth plus 0x to the fourth minus 2x cubed plus 4x squared minus 3x plus 1 and x minus 2. Now, our general process is going to work the same way it did before. I'm going to take my leading term and I'm going to divide it by this leading term. So 6x to the fifth divided by x is going to be 6x to the fourth. And then I'm going to multiply 6x to the fifth minus 2 times 6 is 12, x to the fourth. And then I'm going to subtract, which means I have to flip that sign, and I bring down 12x to the fourth plus 0, and then my next term. And then I repeat. So this leading term divided by this leading term is going to give me 12x cubed. And I'm going to multiply by x, 12x to the fourth, minus 12 and 2 is going to be 24x cubed. And I'm going to subtract, make sure you distribute. Negative 2 and 24 is going to be 22x cubed, and bring down my 4x squared. And then leading term divided by leading term, I'm going to get 22x squared times x, 22x cubed minus 44x squared. Distribute the minus so that I can add 48x squared. Bring this down because I need more space. Bring down my next term. And then again, I divide leading term by leading term. So up here, I'm going to get plus 48x and multiplying by x, 48x squared. And 48 times negative 2 is negative 96x. You can probably tell for a while now that this is not going to divide evenly. Subtract, make sure you distribute. Now add, this is going to be 93x plus 1. X goes into 93x. 93 times plus 93 and 93 times x, 93x, 93 times 2, 186, so minus 186, distribute, and you end up with 187 as the remainder. That was a lot of work. Let's try the same problem again, but with synthetic division. And you'll find that one of the advantages of synthetic division is that it's going to take up much less space. So we're going to still set up our synthetic division using our leading coefficients. So we had a 6x to the 5th, and then we had a no x to the 4th, and then we had a minus 2x cubed, and then a 4x squared, and a minus 3x, and then a 1. And the thing we're dividing by is x minus 2, so it's a 2 that goes out here. And now we bring down the 6, and then we multiply and add, and then we multiply and add. Nope, that's a positive. And then we multiply and add, and then we multiply and add, and then we multiply and add. So again, here's our remainder. It matches our long division. And you'll notice that each of our terms down here does in fact match our polynomial solution from before, 6, 12, 22, 48, 93. And that is the same polynomial. Remember, this would start with 1 degree less than we had before. So instead of x to the 5th, this is 6x to the 4th plus 12x cubed plus 22x squared plus 48x plus 93, and a remainder of 187. Now, one other scenario that we might worry about is, what if we have to divide by a linear term, but the leading term is not an x, it's 2x or 3x. So let's look at an example. 12x squared plus x minus 4 divided by 3x minus 2. Now, the long division part doesn't change, but we do have to modify the synthetic division. We cannot divide by ax minus c. It has to be x minus c. And so what we're going to do essentially is we're going to factor out the 3. So 12x squared plus x minus 4 divided by 3 times x minus 2/3. Now you can see if I distribute this 3 back through, that I will get x minus 3x minus 2 back. But my 0 is at 2/3, and so that's what I have to use with my synthetic division. And then after I've done my synthetic division, I can factor the 3 out of whatever polynomial is left in order to turn my factor back from x minus 2/3 back to 3x minus 2. So let's actually look at that example. So again, I'm only going to do this with synthetic division because the long division process is exactly the same. You just have that 3x that you're multiplying by in your leading term. So the fractions do make this a little bit trickier. 12, 1 minus 4. And then this is x minus c, and c goes out here, so we flip the sign. So 2/3. So I bring my leading coefficient down, and then I multiply 12 by 2/3. Now, 12 by 2/3, the 3 is going to reduce. 2/3 times 12, I'm going to end up with 3 canceling and leaving me a 4 times 2 is going to be 8. And then I add, and then I multiply 2/3 times 9. Again, my 3 in the denominator is going to cancel. It's going to leave me with a 3 times 2 is going to give me 6. And then I add, and I get 2. So this doesn't divide evenly either. I have a remainder. This is going to be 12x plus 9. And so what I can do is I can take my 3 out. 4x plus 3. And so that can leave me with the 4x plus 3 is the result of dividing 3x minus 2 and not just x minus 2/3, because this 3 can now cancel with the 3 that's in the denominator. That extra factor is something that you have to keep in mind when you have a leading coefficient of x. But that does not affect the remainder at all because this won't divide evenly anyway. Now, the last thing to kind of keep in mind, synthetic division is absolutely great. If with practice, you can get very, very fast at it. The thing that you have to make sure that you're not doing is ever trying to do quadratics or other pi-powered terms. Dividing those out is going to be a problem because synthetic division is designed to work with linear factors, not quadratic factors. When you can occasionally apply it is if you are dividing by, let's say, like x squared plus 4, and you can do a substitution in your numerator to replace all of your powers with powers of x squared. So if you have only even powered polynomials, no odd powers, then you can do a substitution. You can turn your expression into something like a linear factor, and then you can do it. But you can't do it if you have like x squared minus x minus 2. That's got an x term in it. You can't do that. You have to do long division. If you have any linear terms or cubic terms or anything like that in your numerator, same problem. You can't make the substitution u equals x squared, for example. And so you're not going to be able to convert it to something where you can, in principle, do synthetic division. If you encounter any of those scenarios, you have to go back to long division. Synthetic division is, again, it can be very nice, but, and we're going to see in some other videos, other things that you can use it for, because you can actually use synthetic division, quote unquote, for calculating the value of a function, because it turns out the remainder is the value of the function at when you plug in that value. The problem is going to be that it only works for linear factors. And so it can be great, but it is limited in its application. Long division, you're never really going to be able to get away with it. Like pretend that you don't ever have to know it again, because there's always going to be circumstances where synthetic division can't apply, and you're going to have to fall back on long division. So both of them have their advantages. If you can do long division, in principle, you can do every division. But as we've seen, it takes up a lot of space. It can take longer than synthetic division. And so having both tools in your toolkit really is extremely useful.